Hey folks, we're going to start talking about magnetic fields, and we're going to introduce something called the Biot-Savart law and at least talk about it in a conceptual level. So in the last unit, we did briefly talk about magnetic fields, and magnetic fields are one cause of them, and the one we're going to study in this chapter is moving charge. So moving charge creates magnetic fields around it. Okay. So let's say we have a wire, and here's your wire, and let's say it's carrying a current that way. Okay. Well, that wire, that current, is going to produce a magnetic field around that wire. And we're going to look at one particular point. We'll look at this point right here. We'll call that point P. And we're going to look at one little tiny chunk of the wire, this little chunk right there. Okay. We'll call the length of that chunk ds. So that's the length of that little chunk of wire. And then this would be the radius from that little chunk of wire to our point. This would be the angle between them, which is not 90 here. It's a little less than 90. And how does the magnetic field over at point P there, what is its direction and what is its magnitude given all this stuff? Okay, well, Biot-Savart, they came up with the following, they figured out the following ideas. Letter A, the magnetic field, which is, we use a letter B, so the little chunk of the magnetic field made by this little chunk of wire is perpendicular to both the current and the radius. Okay, so if you look at the current, which is kind of going up and to the right, and the radius here, okay, what direction is perpendicular to both of those arrows? Well, it's either got to be into or out of the page. Now, in a little bit, we'll do some examples with direction on this, and we'll talk about, well, which one is it, into or out of the page. But the magnetic field at point P is either out of the page or it's into the page. It's one or the other. That's the only two directions perpendicular to both the ds and the r in this case. All right, other things they figured out. The magnitude of the dB, okay, is proportional to sine of the angle. In other words, it's a cross product. And it's going to follow a right-hand rule, which we'll talk about the direction in the next video. Okay. The other things they figured out is they figured out the magnitude of the magnetic field is proportional to the current, which kind of makes sense, right? The stronger the current, the more field you're going to get around the wire. Okay. Another thing they figured out was they figured out the magnitude of the magnetic field is proportional to the length of the wire. Okay, so if you have 1 inch of wire, have a current of 1 amp, you're going to get a certain field. If you have 2 inches of wire with the same 1 amp current, you're going to get double the field. Okay, and finally, the last thing they figured out was the little chunk of magnetic field is proportional to 1 over the radius squared. Surprise, surprise, we have our inverse squared law. A lot of things follow the inverse square law. Okay. All right, so what Biot-Savart did was they put all this together. Okay, so here's how they put it together. dB, okay, is equal to a constant, mu naught I over 4 pi. Now, mu naught, by the way, and I'll mention this, and this will come into play later, mu naught is equal to 4 pi times 10 to the negative 7th. Okay, now, and then the units are Tesla times meters per amp. Okay, now you might be looking at that and going, well, Mr. Mashar, if I put the 4 pi and e negative 7 up here for mu naught, won't the 4 pi's cancel? Yes, they will, but you'll see why we have this in there in a little bit. Okay, so it's there. And then, so that's a constant out front. We've taken care of letter C here. We've got the I in there, proportional to I. And then we have ds cross r hat. Okay, so we've taken care of the direction. It's perpendicular, it's a right-hand rule. And then the sine of theta is going to be in that cross product. Okay, we've also taken care of this. ds, the magnetic field is proportional to the length of the wire. And then we divide this by r squared, and that takes care of letter E there. So that's our equation. Now, the r hat, that is a unit vector. Okay, its magnitude is 1, and it is in the direction of r. Okay, so it's not the radius, it's just the radial direction. Okay, so be careful with that. Now, we then add up all these chunks by integrating. So your magnetic field, okay, will be mu naught I over 4 pi integral ds cross r hat. That usually involves an angle, sine or cosine, over r squared. This is the Biot-Savart law. Now, depending on the year, we might do a bunch of examples using that equation. It is not an easy equation to use. You're integrating. You have a cross product. You have to worry about an r hat. You do have an inverse squared law. So all those things do make this equation kind of difficult to use. So depending on the year, if we have time, we will do a bunch of examples with this. If we don't have time, then we're going to leave it at you understand conceptually what's going on with the magnetic field up there. Okay. Now, in the next video, we will focus on the direction of the magnetic field around this wire. Okay, which way, at point P, we know the field is either out of the page or into the page. Well, which one is it? We'll do a few examples and talk about that. All right, so for now, that'll do it. I hope that video was helpful, and thank you very much.